Well, good morning, everyone. It's really good to be here. I always enjoy coming to California because this is where I have my degrees from, and spent a lot of fun years here. So I can remember sitting in your seats a number of years ago. And in fact, as I was walking through the quad here, I actually got married in the church here more than 32 years ago. So it's a little bit. My discussion with you this morning is really to kind of give you a very broad picture of kind of how we view the world in the Department of Energy's National Energy Program, and specifically some of the things that are going on at the National Renewable Energy Laboratory, which, as the director, I have the great honor and privilege to lead. As you can tell, I'm here, they're working there, so I don't do much of the day-to-day stuff, but I get a chance to run the country down, run around the world bragging about the things that they do. But I do want to give you a broad perspective of what challenges we are facing and how technology plays a role in that. And for those of you that are not in the technology profession, more in the business and legal professions, also how policies and markets actually relate to all that. So I'm going to go quickly through these. And by the way, these charts will be on my website, and I think probably Dan will put them up on their website later on, so you get a chance to look at these. I just want you to really absorb the broader messages in some of these pictures. So let me just start with energy context, and then I'll leave some time at the end so that we can actually ask a few questions, and I know that there'll be many when we're not done. It's a complicated area. There's really a lot of pieces to this, and you wonder sometimes how come we can't make much progress in some respects relative to our energy future, and why there's so much debate and discussion, and in a lot of cases confrontation about things. And let me try to explain that to you a little bit. Let me just start with what an energy system really is supposed to provide is really three things. It's supposed to allow you to essentially have energy security, or to have access to energy, a variety of different pieces of that, to be the engine for economic growth, economic competitiveness. It actually does drive the economy. And then ultimately, your energy system needs to be environmentally sustainable, if you will, or at least respectful of what implications it has on the environment. And the problem that we have with our energy system today is it doesn't do all three of these things to the degree that we would like it to. And as a consequence, we're always trying to figure out how do we make it be more responsive. I put this as a Venn diagram primarily because you have to address all three things simultaneously. We many times don't do that, and as a consequence, we will sub-optimize. So let me go to the next one, which is kind of the premise. The premise is we have a system that's on the left. That's the attributes of the present system. And I think everyone will agree that we would like to be able to get to this set of attributes, which is on the right, which is essentially a sustainable energy future. Okay, so that would be the end point. That's what we'd like to have. And if you can get all these things, that would be success. And frankly, we should be technology agnostic. If any technology can give you these attributes, we should be happy. That should be the success factor. And as a consequence, it shouldn't be a technology trade-off or a pathway trade-off. It really, can you get to these attributes or not? And if so, can you do it cost effectively, yada, yada, yada. You get to that point, and then that's success. So this is the premise from which we start. The challenge is, how do you go from the left side to the right side? That's the challenge. How do you go from there, and at what pace? How quickly can you do that? All right. So that's really the challenge, and that's really the issue. There's a lot of things about the energy sector that make it challenging. And let me just say a few. There's books written on each one of these quadrants that I have on this chart. So I'll just go quickly. On the far upper left-hand corner, that's R&D investment in the sector. If you look at R&D investment in the sector as part of sector sales, it is a minuscule part. It's a little bitty piece. For contrast it to pharmaceuticals, which is like in the 20%, you have less than 1%, that's 0.3% of the sector sales are invested in R&D for innovation, both on the public side and on the private side. So that's all in. Right? So the sector just does not attract a lot of innovation, if you will, or investment innovation. On the right-hand upper corner is asset utilization. We have an infrastructure today that is very inefficient, and by that I mean it's idle most of the time. Our electricity system, which is made up of all the generators, transmission wires, and all those kinds of things, there's about $2.5 trillion of investment. At any one time in the course of, on an average year, we will only be using half of those assets. So the asset utilization is less than that 50%, it's like 47%. And as a business model, that's a really bad business strategy. Now, there are good reasons why we do that. We like the idea that we have reliable energy, so we plug in the cord into the wall. We expect that energy flows, and we want that to be reliable, and so we build a lot of assets in order to be able to meet the demand that only happens a few times during the year. And as a consequence, you have a lot of it that's idle. So that's the next big piece. On the left-hand bottom corner, this particular sector is incredibly capital intensive, meaning that big investments get made and then they last a long, long time. So for instance, a nuclear power plant, we started commissioning nuclear power plants in the 70s. 30 years later, they were all commissioned for 30 years. We extended them. Now we're extending them to 60 years. And there's work going on in the Department of Energy right now where we'll extend those another 30 years. So all of a sudden, we've made an investment literally that's a century long. So decisions we make today last a long time. And that's true not as long as nuclear power plants, but coal power plants, natural gas power plants, and even renewable power plants. They last a long time. That's the key point. And then finally, over here on the right-hand corner, everybody knows, most of our energy economy, if you will, is highly regulated. It's regulated in this country, and it's regulated in every country in the world. And as a consequence, what you get is distorted market dynamics. And so there's a whole bunch of other things that relates not pure supply and demand kind of economics, it's something very different. And as a consequence of public policy, you get a whole bunch of other things that are in play. All right. I talk about it a lot. The latest thing that everybody's talking about is natural gas, right? So what about natural gas? So you've been reading the papers and you've been doing what I'm doing, and you say, oh my gosh, this looks like it's really a game changer. Well, I think it is. I think it is a game changer. Not that we found a lot more natural gas, we just found a way to extract natural gas effectively and efficiently, and actually able to get it at a reasonable cost. In fact, projections are very low cost. So Tom Friedman, if you read Tom Friedman's stuff by one of the writers at the New York Times, essentially made the statement that it could be. And his little qualifier at the end says, if we do it right. And that part is actually very important, and I think, again, has lots of implications for what we do in the future. The if we do it right part has two, there's a question. One of two scenarios could possibly happen. One is that natural gas would be a bridge to help us to get to, from the left side of that chart that I showed to the right hand of that chart, and then help us get there more quickly. All right, that would be a good thing. The second scenario might be that it postpones our motivation, our investment, and our desire to go from the left to the right more quickly, and then we actually lengthen the time that we do that. The fact of the matter is, natural gas is not a clean technology. I mean, it is relative to the other things that we burn, but it's not by itself the answer that we're looking for. I'll get back to that here in a minute. So what's happening already in the electricity sector is that if you look at, this is just historical, so this is just data. What you find is that, nuclear's been kind of flat, petroleum, not surprisingly, is coming down. Natural gas is moving up. Since 2008, we've gone from 21% of our mix to 27% of our mix, natural gas, and it's moving very rapidly. And actually, surprisingly enough, even renewables has increased, continues to increase. The real loser in this area, or in the displacement and the change, is coal. Coal used to be on an annual, on a domestic entire country basis, it was 48% of our electricity mix. Now it's 38%, and that's diminishing rapidly. So much of what you see in terms of who's getting displaced, it's coal. And there's a variety of reasons why that's occurring. But you'll hear that debate in the news. The one other thing I'll point out is renewables. So renewables is about 13% right now, which is actually a lot more than we used to have. When I started, at NREL in 2005, we were like 5%. Now we're 6 or 7%. Most of that being hydro. Now we're at 13%, and that will continue. Most of it's hydro, as I mentioned, and the other is all the non-hydro renewables, which is also a growing, in fact, important part. In terms of capacity, the capacity of our electricity system right now is about a terawatt. And as you can see here, coal is 30%. It was, remember I said it was 48 and then coming to 38%. That really is because coal generates more energy on an annual basis, even though it's only 30% of the mix. Capacity-wise, on a generation side, it's more like 50% of the mix because the capacity factor, it's operating more of the time, which is another dynamic that you have to play in this arena. The interesting piece is here's what we have today. We're going to add about another quarter of our generation asset over the course of the next 25 years. More than half of that will be natural gas, and another about a third of that will be renewables. And then there's a little piece that'll be on everything else, and that actually is going to be a replacement of what's going on over here. And the growth actually is actually relatively modest in terms of the demands in this country. Now, that's not true in Asia, and that's not true in other parts of the emerging economies. But that's what we have here domestically. And that also portends the fact that there will continue to be, and this is now a focus on renewables. If you look at renewables, what you'll find is kind of we're right here. This is 2010. So we're right here at this point. And this point right here this is an EIA projection. What they're suggesting is that over the course of the next few years, one of the things, there's a thing called the production tax credit that subsidizes wind technology when you deploy it. And that's going away. That's expiring at the end of this year. And if it doesn't get renewed, then what you get to is instead of this slope of renewable penetration, you get this slope. So the message here is renewables isn't going away. It isn't going to stop, but it's going to slow down. I mean, that's what the EIA would project. Now, I might add that the EIA is an agency within the Department of Energy that does these analyses. They do all these economic analysis. But frankly, what they do, and this is my analogy, but my metaphor is that they're kind of driving the car by looking in the rearview mirror. It's like, what have we done today? And then they just kind of extrapolate that. Okay, so that's not necessarily what the future needs to be. It's just what if things don't change, that's the trajectory we will stay on. All right, so that's how these projections get made. And I would encourage the economists in here to think more holistically about what do we want the future to look like and get to that. And let me now talk about that. One more thing on natural gas, and I'll come back to that. So remember I mentioned that the Venn diagram. I always start with that because there's this piece called environment, and in the environment piece there's a thing called emissions and greenhouse gases and CO2 emissions that are actually important. I chair the National Science Board. It's the agency that oversees the National Science Foundation, and we have the oodles of science capability, $7.5 billion of work that we do. One of the things that we do is we look at climate science. And if you look at climate science in any detail, it is very clear that the climate is changing and it is man-made. Okay, so I don't know how else to say that other than just say it bluntly, and the science supports it. And there's no debate about it among the scientific community. And if you go look at stuff, if you go to the North Pole or the South Pole, which I have done, and you look at what's happening, it is absolutely dramatic and stark and life-changing. So just to tell you, from someone who has experienced what I think is those in the higher latitudes, climate change is real. So if you think about climate change and you think about CO2 emissions, one of the targets that we have, and we've signed up for this as a country, is that we want to reduce our greenhouse gas emissions, to 80% less than 2005 levels. And MIT did a study on natural gas and its future, and one of the charts out of that study is this one here, which shows that natural gas will expand. It'll displace coal in this case, and then along about mid-century, if we want to make the targets of the 80% below 2005 levels of greenhouse gas emissions, you literally have to phase out natural gas in the way in which we use it today, and we have to replace it with this big green area, which could be anything non-carbon emitting. So that could be nuclear, that could be fossil fuel with carbon capture and storage, or that could be renewables and efficiency. But somehow you have to make up this whole thing with some non-carbon emitting source of generation. And that's the bridge part of the discussion about natural gas. So unless we're thinking about this state, and remember how long these investments take in terms to play out in the marketplace, unless you're thinking about this end state, we're not going to get there. And if we think, oh, let's relax, we're problem solved, now we have abundant domestic energy,
we've really missed the boat. We've squandered an opportunity, in my opinion, an opportunity that'll be very helpful, and it'll be very damaging to us in the future if we don't do that. Okay, so I get asked the question lots of times. So how much can renewables actually? I mean, you know, we've been at it a long time. Nothing really moving very quickly. How much can we really get, and is it economic, and could we really deploy it if we wanted to? Well, up until recently, no one was willing to even ask the question, let alone do the study. All right, so we've now asked the question. We've now done the study, and one of the things that I got, you know, a lot of criticism for is I've made statements about the potential renewables, and somebody says, well, there's no credible study. Well, there actually is a credible study. We've had over 35 organizations, and using the most sophisticated tools that we have in terms of how do you both generate energy and how do you distribute energy to the load centers in the U.S. under the conditions that we presently have. In other words, looking at our infrastructure today, looking at how energy gets dispatched, which means, you know, essentially where's the lowest cost generator and how do you meet a load and all those kinds of things. There's all these very sophisticated tools. All these people got together and they did this study. It took about 4 years to do it. We looked across the country and looked at where are the resources. So they're everywhere. It's kind of what the conclusion is. And there's plenty of resources. It's not a question of how much resource do we have. There's plenty of resources. And then we looked at where's the transmission, what will the load look like in terms of growth over the course of the next 40 years or so. By mid-century, what is it going to look like? This is what it looks like. And the conclusions of the report are that, and we did this parametrically. So we said, so if you wanted to generate 10%, what would it look like? You don't want to get 20%, 30%, 40%. This report is not a prediction. It's not a projection. It is an analytical study of can it happen? Can you actually do it? And so we went all the way up to 80%. Can you make 80% of our electricity generation from renewable energy? That was the question. And the conclusion was, yes, we can make 80% of the energy in this country from various forms of renewable energy with the power system that we have today, with the technology as it is today, no breakthroughs, no major things that have to change. What does have to change is we have to have more transmission. We have to be able to get the energy from where it's generated to where it's used. But for the most part, it isn't something that is impossible. In fact, this is a simulation and a calculation year by year of where the generation is, and the various colors are the different kinds of renewables, and you can see where they are. And this is an annual thing, so it kind of pulses a little bit to show you how much it's growing on an annual basis, and then how much you use, and then you have the seasonal variations. And we did the simulation all the way out to 2050 and showed what it would look like, where in the country it would be generated, how it would be used, how the energy flows. This is a very, very comprehensive report with all of this detail. It's the most detailed study that I've seen to date. But the conclusion is, this is worth studying. There's something here that we can take advantage of. It's not that it is the future that we predict, it is the future that's available to us. It's a future that we can aspire to if we just chose to. Now, it's not a matter, again, of do you have the resources? Does the infrastructure accommodate it? Do we know what we need to do? We can answer all those questions. This is an analytical scenario discussion and assessment. And in fact, the bottom line is you can do it. So it really is about what kind of investment do you want to make. It is about markets. How do you deploy these various technologies? And ultimately, how do they get integrated into a new future that's very different than the future that we have now? Now recognize that the EIA projections, they don't say this. They say, okay, we're going to be on this track that we are, and we're at 14% now, and if we work really, really, really hard, by 2035 we'll be at 15%. So I'm always, kind of the pragmatist about this. I say, so what is it that, why would we want 15% instead of 14%, and why can't we do more? And so a lot of that has to do with these things here. It's really a lot of investment required that make that work. Let me just talk about technologies a little bit, and I'll come back to the endpoint, and then we'll ask some questions. I'm not going to go through this in any detail because I think many of you can go look this stuff up, but mostly photovoltaics, that's kind of one of the big flagship programs within the Department of Energy. It's the glamour child. That's the one that everybody focuses on. It's really cool science. Sunlight in, electricity out. It's great stuff. Solid state. Great physics. Lots of great science going on. And one of the things that got me interested in the field literally 30 plus years ago And we're making progress. You know, we're at 4 gigawatts here. You know, I might add, Germany's at 18 gigawatts, and they've got the sunshine of Anchorage, Alaska. Now, you know, it's going to say, well, how does that work? Well, the reason that works is because they also have energy prices that are like 30 to 35 cents kilowatt hour, where we have energy prices that are down between 5 and 10 cents kilowatt hour. That's a big difference. It's a big driver. And so even though they don't have much sunshine, this actually makes sense in Germany, more so than it makes sense here in many parts of our country. It does make sense in some parts of our country. And so that's the point that I want to make. Lots of great science. For those of you that are working on science degrees or engineering degrees, lots of really cool stuff here. This is our biggest program at NREL. And in fact, you know, as I look in the lab, there is more exciting stuff going on today than there's ever been in the last 30 years of my professional experience. We've got some great work going on, even with Stanford and with SLAP. We just won a couple of awards that we're doing using the big synchrotron that you'll see, I think, later today. It's about materials and about materials understanding, and we're starting to get sophisticated in understanding how to manipulate essentially the various properties and the physics of materials so that they provide us the kind of service, the kind of capabilities. Great opportunity for innovation. I expect this to continue. I won't go through this in any detail other than to say there's some great science and material science, engineering science, and a lot of other things that go with that, along a lot of different types of technologies that we can aspire to. And I'll be happy to talk about the details of any of these with anyone if they're interested. Wind is another to me, it's one of the more interesting. I'm a mechanical engineer you know, worked in thermosciences and fluid dynamics and those kinds of things. These things are just, they defy logic. You know, when I started in the business literally 30 years ago, the largest wind turbine was 1.8 meters in terms of wingspan, in terms of the swept rotor. These machines now, I was just in Germany at a plant, not in Germany, I'm sorry, in Denmark, at a plant that where Siemens has their new R&D center. They've got a 6 megawatt turbine. The swept area of this thing is 120 meters. Okay, that's well larger than a football field in terms of the swept area. The nacelle, this little piece right here, this is the part where the gears are that after the blades turn and they turn the motor and they get you some inductive electricity coming out of that thing. That thing weighs 250 tons. And so you wonder, how does the wind actually move this stuff? Well, it's incredible. It does, and it's, you know, we've already got an incredible amount. We've got like, you know, 50 gigawatts, 1,000 megawatts in this country. A lot more internationally, a couple hundred gigawatts in terms of international deployment. And the costs are really coming down. They're getting to be where they're almost competitive with the traditional fossil fuels before the natural gas revolution. Okay, so we've made a lot of progress and lots of great things are happening, and there's just, again, a lot of really cool stuff that's going on. And one of the things I like to show is that we are now looking at these fields as systems. And so you look at the entire energy that's coming out of a wind farm, so typically 200 or 300 megawatts at a time, sometimes up to 500 megawatts. And what you find is that the field underperforms. And part of the reason it underperforms is that when one turbine is sitting in front of another turbine and the wind blows directly downstream, as you see here in these various pictorials, this is an actual measurement, and this is the simulation. What you see is actually the energy taken out of that wake from the first turbine, creating the wake, actually will reduce the power output of the second turbine by as much as 60%. So all of a sudden now, this is kind of a systems level problem, and one of the things that we're doing is we're, for the first time in my career, looking at these things as a system, and we're beginning to calculate, and this thing will load in a minute, we're beginning to calculate the energy output of each of the turbines from first principles. We're doing these large eddy simulation models for those mechanicals in the room, and then looking at those things from on the basis of how do they affect the downstream flow of that wind. Now, the wind won't always blow in one direction. Obviously, it blows in many directions, and so you have to now integrate this effect across the way in which the wind varies over the course of a year. So here you see a turbine, and this is all from first principles calculations, where we've never done this before, believe it or not. And now we're looking at it first from the single turbine, and then we're putting in an array of turbines, which you'll see here, that this simulation is an array of turbines And then ultimately we look at the entire field of turbines. So this is the single turbine. Now we've got an array of turbines, and we're looking at what are the downstream effects of the upstream turbulence on those. Turbulence, again, reduces the energy content, but it increases the load on the blades. So these blades are made out of fiber type of materials. They're not steel. They're composites. And as over the years, they will in fact have a great deal of load stress to them. So one of the things that we're worried about is how can you essentially design these systems to be more compliant, to cost less, because we're really trying to reduce the cost even more now than we have in the past. And you have to do this from the first principle. So we have high-performance computing and a lot of really, really sophisticated tools to help us get to the answer to that. That's a kind of a very cool study, which we're very, very happy about. There's lots of other renewable energy generation technologies. There's geothermal, which is also a very viable technology. There's hydrokinetic. There's a number of others that deal with other forms of extracting energy. I just talk about the big three because, frankly, that's really where most of the work is done, and where most of the first entry will happen. But eventually, we need them all. Let me just say a word about biofuels, because that's another big part of our energy economy. It's not just about electricity; it's about transport. It's about how do we do, essentially displace liquid transportation fuels. A lot of great work going on in biofuels. And so the biosciences is a huge, huge deal. So chemistry and chemical engineering and those kinds of things begin to really flow into this thing. And somehow, just the way the system works is that you also get caught up in ag policy, because, it started off with helping the corn farmers in the Midwest, and that's great stuff. But that's not energy, that's ag, and anyway, all of that gets muddled together in our political system. Ultimately, you start dealing with ethanol, and ethanol is important, and it's a good fuel, and in fact may have a bigger role than many people think. But it's not really about competing fuel with food. It's really about cellulosic or the other forms of biomass and turning those into types of feedstocks that can help us. The next big thing, though, is how do you do drop-in fuels? How do you use the existing infrastructure, which is a huge amount of investment, so that we're in a position where we can take the biomass and convert it and then drop that fuel into existing refineries and use it in our cars and trucks, just like we have the regular petroleum fuels. And how can we do that more efficiently, more effectively? And in fact, we've got a bunch of technologies that are very, very cool. Again, very sophisticated technology that's going on in terms of understanding how do you deal with the deconstruction of biomass. Biomass is these long chains of carbons and hydrogen and oxygen molecules that are typically, can be converted to sugars, and those sugars actually can be then fermented into alcohol, or in this case, we're now fermenting them into molecules that are more like our own hydrocarbons. So one of the things that we're doing is we're doing some really basic modeling and understanding of how enzymes work and how essentially these organisms attack. In this particular pictorial, this is another simulation calculation. The blue strands are microfibrils. Those are what you find in plants. And these enzymes or cellulosomes are groups of organisms that attack the external surface of those to start to deconstruct those molecules so that you can make them into smaller and hydrocarbon-like molecules, either sugars or fermentable things that you can turn into hydrocarbons. And this is a calculation of essentially the crystallography of the thermodynamics, if you will, of these organisms. What allows them to do, these enzymes, is essentially what insights we get from that is that they wrap around the microfibrils and cut them loose from that. When I started literally 8 years ago at NREL, we did not even know this, and this is really new stuff. Again, a lot of great science that we're adding to it, and it allows us to then manufacture and otherwise breed biomass in ways that allows us to deconstruct it and put it into our energy mix a lot more efficiently, a lot more effectively. A lot of great stuff going on there. I would be remiss if I didn't talk about efficiency, because one of the keys to improving our energy mix on the generation side is making everything a lot more efficient. We are so inefficient, it's embarrassing. Our system wastes roughly 2/3 of the energy content in its initial state by the time we get to use it for some service that we care about. Mobility, heat, comfort, whatever that service might be. And we've got to do a lot better. Transport, no one can deny the fact that we've got an inefficient transport system, all right, and that includes all the discussion about private transport versus public transportation, those kinds of things. Lots of things can be done. It's not we're devoid of innovation. We can innovate. And to the administration's credit, one of the things that we've chosen to do as a country is to set the standards higher. So instead of 27 miles per gallon, which is where we are now, now we're saying let's double it. Let's double that by some reasonable amount of time, 2025 or whatever. And that would go a long way. I mean, if you think about it, you double the efficiency of the automobile transport sector, and you cut in half the amount of energy that you use in that sector. I mean, that sounds like a pretty good deal. So all of that to say is there's a lot to be done here in this sector. And for a lot of reasons, we don't do that. I'll get back to that here in a minute. Buildings is another one. Buildings are incredibly energy intensive. Something like 70% electricity is used in buildings, both residential and commercial. Some very, very large fraction, 40% of our overall energy consumption, it goes into buildings. And we can do so much better. And in fact, take a moment to look at this. Look at commercial buildings. It's about 20% of overall energy usage in the country. A lot of it is lighting. We live in a great part of the country here in California, and the sun is out most of the time. You get a great sunny day today, and you haven't got all the lights on, But what's up with that? So there's ways to do this differently. And so one of the things that we're looking at is what are all those things that you can do? And there's lots of them. One of the questions that keeps asking, why don't we automatically just do that? Well, there's a lot of reasons why we don't do that. Well, one major reason is there's this thing called decoupling. And what it means is that we've got the people that build the infrastructure, the constructors, they build to a spec. The people that live in the infrastructure, they actually pay the bills. So the constructor has no motivation. They put extra money to construct. It's, or the developer, they don't really care. It's the tenant stuck with the bill. They could care less economically about how it looks, how it functions. They care about how it looks, unfortunately, more than they care about how it functions. The important part, though, is we can do something very, very different. If you were to add up all of these things, and I'll finish here in a minute, you can do things like what we've done at the National Renewable Energy Lab. And we have this building called the Research Support Facility. It's really where our researchers sit, many of us. And my office is right up here in this little cubby right there. We have 1,350 people in this building. On an annual basis, when you include all of this, and there's 2 parking garages that go with it, and they have photovoltaic panels on the roof as well. When you include all that, on an annual basis, it generates as much energy as it consumes. Okay? It's net zero energy. Now, how do we do that? Well, the first thing we did is, you see the layout of this building? This building is 100% daylit, meaning that when the sun's out, you don't have to turn on the lights. You can. We got lights like everybody else, but you don't have to turn them on. So you walk to the building, and most of the places where people work, you don't have lights on. And that's so we did this. This is east-west kind of orientation. North is this way here, and we figured out you can throw light about 20 meters, 60 feet. So these quarters are 60 feet wide and long, and then you got all the shading and the things that you do for natural solar. We put everything we know how to put into these buildings to make them ultra efficient. They are about half of the energy efficiency or half of the energy usage of a building built to code in the Denver area. And ultimately, after you do all those things, it's really efficient. Then you put on the renewables, and now you can essentially balance all of that energy. The great news about this building is, and the first question I always get asked is, that's great stuff, and it may be good for you, but how much extra did you pay for that? Because we don't always have extra money. Well, the interesting piece is we actually paid less for this building than the budget that I was given. We paid less for this building than a building built to code. I had a $300 per square foot budget. We built the building for $259 a square foot. You add the photovoltaic panels, it's $286 a square foot. And after we built the first phase, this phase here, we built this one for $17 a square foot cheaper than we did the first phase. We learned a lot of things in the process. This is now an iconic building. This is the world's most efficient building at this size. And LEED Platinum and yada yada, all those things, multiple awards. It can be done. That's the point. It can be done. Now, it turns out that we paid for it and we live in it, so we were very motivated to make sure that it didn't cost us a lot going downstream. And the last thing I'll say is 30% of the building functioning is the occupant behavior. It's like us, how do we operate in that building? And we're very attentive to that. We've got little icons that come up on our computers and tell us, now's a good time to open the windows, close the windows, do the things to interact with the building that allow you to do that. So there's a lot that can be done there, and I encourage you to look at that. The last thing I'll say is in building integration. Building integration is really about how do you, or energy integration, how do you put all these pieces together to get to this future that we want? And I won't belabor this, but to say it is a system and it's highly complex and it needs to be balanced in a lot of different ways. And it's really, this is the current system, this is the current system where you've got essentially big power plants, big wires connecting everything. This is the future system. It's in a distributed model. And the distributed model is really to take advantage of that building I just described, so that not everybody is demanding energy at the same time when it's real hot outside and everybody's got their air conditioners on. In our case, when at that point in time, we're exporting energy back into the grid. Now that's a huge deal for those that are trying to build more power plants because you need to service that peak load a few hours of the week, of the year. And we're in a position where we get back energy during that time. We're in a position where we can help solve that problem by putting distributed generation in at the local level. So all of these things are there to be part of that. We've got a new building that's going to help us kind of do the science and do the research that helps us investigate how do you do that in an effective way. This is the last thing that I'll talk about is really the energy system. It is really the integration of all these technologies, and this new system, this new building we have will bring together all of these various viewpoints, vendors, developers, utility executives, transport folks that can help figure out how does this all wire together. How do I get to that future that I talked about at the beginning that ultimately we would desire to have, but probably it's not going to happen unless we do something proactively. And a lot of stuff that's going on with this. I just show you this because it's one of the things that we'll do. We'll import a lot of data. This is a simulation of a residential PV system in SMUD, in the Sacramento Municipal District. And this is a cloud coming over, because one of the things that people always talk about, well, you've got this intermittent resource, the sun doesn't shine, clouds come over, all these kind of things. Here's a development, it's a real development, real data. What we're looking at is in each one of these little feeder stations for several homes, how does the voltage essentially react as the cloud comes over? And so we're looking at how do you deal with that, and how do you then do the voltage support that's necessary to make sure that if you did this on a really broad scale, it doesn't bring down the system, doesn't make the system unreliable. So it has really more to do with how do I incorporate, how do I essentially actively begin to change the energy portfolio using as much of the renewable resources as I can, and not letting it be a barrier, being part of the solution, not being part of the problem. So that leads you then to this conclusion then that really we've got a couple of options here. We can kind of continue to do business as usual, or we can aspire to a new future. It means we have to invest in innovation. This country is great at innovation. This country is, I think, good at vision, and we need to think about what future do we want and aspire to get to that future. It really is about the money. When you get right down to it, it's about who makes the investment, what kind of return on investment you get, and those people that are in the marketplace have to find the value of that. So that's another big component of the market pull versus what we've typically done, which is the essentially policy or technology push piece, where we're trying to make the system work different than the way it normally operates. And then ultimately, this is a global issue, not a domestic issue in terms of energy. Energy is a commodity globally. We tend to focus on it domestically, but it really is a commodity globally. And frankly, the rest of the world's moving out. We are falling behind in lots of different ways. We're still the innovation leaders of the world, but I got to tell you, in all the downstream pieces, the manufacturing and all the other pieces, not so much. And anybody that thinks that the rest of the world isn't moving on while we're sitting still trying to argue about what it is we're going to do is fooling themselves. Because frankly, I've traveled the world and I can give you that from a clear standpoint. So that ends my presentation. I hope that I've stimulated a little bit of questions. And I'm now ready to answer some questions. Thank you. Okay, so now we'll just start and do a bang thing. Let's go.
The 80% on renewables that you find for the US, do you think is particular for this country because of the sunlight or something like that, or if you think the rest of the world can be bigger?
So everybody heard the question? If the 80% for that we did for the study, domestic renewable energy electricity study, would that be comparable for the rest of the world, or what's the do we have unusually blessed resources here in this country? Actually, we have a lot of resources in this country. That would be the first point that I would make. But not all countries are all countries are the same. But most countries, I think, certainly because there's clearly pretty good solar almost everywhere, can aspire to at least 50% or more. If you go to Germany and the Netherlands and most of the parts of Europe, they're aspiring to 100% renewables. I mean, they laugh at us for talking about anything that's less than 20 as being anything other than business as usual. And so the expectation is that globally we can get to some large number. I don't know if it's 80%, but some very large number, much larger than what we have today. Next question. Yes, sir.
With respect to the transmission networks, what is the state of the art, and are high temperature superconductors even being considered for long distance transmission? I mean, what's the growth in that area?
Yeah, so transmission is obviously a big issue, as I mentioned, and there's lots of technologies, and I used to work on high temperature superconductivity, HTSC, a number of years ago. It's still a very interesting technology, and there's certain niche applications for it that make it effective now for small runs and those kinds of things. But what's necessary in terms of the broader infrastructure is just much more efficient. And it doesn't even have to be that much more efficient, but going from AC to DC transmission high voltage is kind of the biggest thing that people are working on these days. And if you just did that piece, you would improve the transmission kind of condition of the country or the infrastructure dramatically. So there's some technology that's still, I think, required, but it's really not about technology for transmission. There you need permeating right-of-ways, how do you move the electrons? That's a lot more challenging because we've got essentially a social/policy regulation issue that's really challenging. Yes, ma'am.
A follow-up question about transmission. What do you anticipate are the costs of transmission to support an 80% renewable energy future? And who do you think should burden that cost? Are the utilities or state governments or federal government?
Yeah, it's a great question. So it has to do with transmission, and so first of all, what's the cost of that going to look like? And then secondly, where should the cost burden be applied? So the study actually does that. So this study, which I just mentioned, I didn't do it justice. It's got 4 volumes, at least that thick on my bookshelf, and it talks about that, and it goes through. And there is a very modest amount of additional investment necessary to do transmission, which you get back, and so it's a net positive, once you don't use the other energy. So depending on how you do the economics, it's a very modest, I think 5 or 10% of addition to the cost per kilowatt hour. The levelized cost of energy is kind of what the expectation is. Transmission is not a big cost factor relative to achieving the other future. Now, the second question is kind of who should pay for that? Well, that's a whole other discussion, and I think there's a lot to be desired, I think, in changing the business models for how we manage our energy infrastructure. And we, like it or not, we've got heavy government intervention. We've had government intervention literally for 100 years. It's served us well. We have decided that we wanted reliable energy, and that we wanted to help those who were exploring and extracting the energy to be much more competitive and effective, and we've done that, and it's a great thing. It doesn't serve us now as well because we don't want to continue to do that. We want to do something different, and so changing that business model is part of that question is who pays, and if it's in Europe they let the ratepayer pay, okay. And we tend to work subsidies through our tax code. That's not a direct link from those using the service to those that are essentially benefiting from what that subsidy really looks like. So that needs, I think, a fundamental relook. I mean, there's a lot of different things that you can do. You can do Band-Aid kind of stuff, which is let's put a price on carbon, cap and trade, price, carbon. All these things are not getting at the real issue, which is the business models that drive private sector investment don't change much just because you have more overlays of government intervention. I think you need a fundamental redesign. Not popular because these things take time. This is decade-long kinds of things. I lived through the Bell system restructuring, in the late 70s, early 80s. That took several decades. I'm really glad we did that because now we have IT communication in a very different way than the way Ma Bell did it. But that will take time, and you're not going to hear elected officials talking about things that take a long time. So that's the unfortunate part. Yes.
So building on this point, how do you make investment across the value chain? So you mentioned manufacturing, for example, more attractive. So from your perspective, what should we do?
Well, again, very, very complicated. And one of the issues that I think I find most compelling about energy is it typically is local. Like politics is local. Right? And the issue here is that what has actually allowed us to make progress over the course of the last several decades, while the Feds or the centralized policy making was non-existent, is local economic development drivers. When a region, a city, a state, a region of the country decided that they want to make, kind of renewables or clean energy or sustainable energy a tool of economic development, they will put the policies and regulations in place and the facilitation to make that become a little cluster and center of excellence that promotes these technologies. That creates jobs, that creates economic development. You get reinvestment. You get lots of things that are attendant to the economic model. And so you need the whole value chain. You just, one thing as a scientist and technologist, there's great science, and oh wow, we just did this. Well, that's the easy part of the problem. The easy part of the problem is that it works. Now it's how do you infiltrate the entire marketplace, create the entire value chain of all the bits and pieces that ultimately provide the service. But it's not just about the technology or the big vendors or the aggregators. It's all the mom and pops. It's the supply chain that feeds that whole model. And so what happens is that models will take hold and they'll take root, a little bit like silicon PV in China, and all of a sudden it becomes this mammoth thing that's hard to compete with because it becomes an infrastructure, it's an ecosystem. And so you need to be thinking through how do we change the ecosystem, because the investment is made along all parts of that ecosystem. Not just when you do the big wow and the demonstration and everybody does a high five. That's not sufficient. And in fact, we've done lots of that where it just kind of group and then it just kind of fizzles because there's just no motivation to move that whole thing. So you get technology into the marketplace. It starts in a niche. It grows, and they reinvest and they build that infrastructure that relates to how do I be competitive in the future. And they reinvent themselves and they keep moving. They become competitive. That's the way it'll work. That takes a long time. Yes, right next to it. Right?
So it seems to me that the distributed or decentralized energy systems are the way to go because it's more reliable, more efficient, and also can stimulate more innovation. So can you have a comment on that? What are the major barriers for the mass adoption of this decentralized energy?
Well, a great question. So this was centralized versus decentralized model. There's lots of. I make the case for the decentralized model. I think there's a balance of both. Obviously, we have to make the transition from a centralized model to a decentralized model. And it's very different. It's very interesting and very different in different parts of the world. In emerging economies, a distributed model, you're not going to build the centralized infrastructure. It's the leapfrog thing. You're going to go to the decentralized model. That just makes more sense. It's got other challenges because again, you don't get the economies of scale. You don't get a lot of the other things that are incumbent in a centralized model. So your question was.
What are the major barriers?
Yeah, what are the barriers to that? Well, so part of the difficulty is we have an entrenched, system. We created this system, 100 years ago. We've got major players who make, just an insanely amount of money. It's a good thing that they're successful, but there's just not much motivation for them to change anything. You really do have to change the model. Which means somebody's interests get compromised here. All right. So that's just to put it bluntly, those interests are going to resist, and that's the biggest barrier. So you got a public awareness issue. So you got a lot of what I would call disinformation that confuses the public. So part of my challenge and the barrier that I see is the public's not very educated. We don't have a very sophisticated electorate. We kind of hear what we want to hear. And then the details are somebody else's problem, you know. And then it's kind of we want the whatever they're giving us in terms of their bottom line, but in fact most of it's not true. It's disinformation. You know what I think is important is that we provide truthful and credible, clear understanding of what problem we're trying to solve. That's not understood by the general population, and I would say even the scientists and engineers don't speak up enough. I mean, we kind of look at it and, oh my God, that's awful. You know, I'm going to go back into my lab and do my stuff because that's, you know, I don't want to deal with that, you know. So you got people like me that's my job. My job is the evangelist, so to speak, and that's my job is to go out and tell people, here's what's possible. We're not going to do this, by the way, unless something really changes. With public awareness, education. I think, again, there's a way to use the existing system. I tend to think that you want the incumbents to be part of the solution, not part of the problem. So engaging dialogue. Tomorrow I'll do an energy dialogue with the oil industry, the gas industry, the nuclear industry, and all that, and say, you know, in a closed room, say, no one, take your badge off, we're not going to quote anybody. Tell us what you really think. Let's talk about what we can do together. Let's talk about, forget the politics for a moment. What would you do if you were, you know, had total control for a day or two? And have those dialogues and understand that what's common among those various perspectives and points of view. That's social engineering, communications, and that is a whole broad cross section of things that we typically don't get, whether you're in law school or engineering school or economic school, whatever. You don't get that. And it's this broader thing, which is why I'm very pleased to talk with this group, because you're thinking that way. You've got some cross-pollination. This problem is really, really complex with all kinds of issues and problems with it. Unless we kind of get together and do it together, you know, we're not going to make much progress, which is kind of where we've been for the last week. Look, over here and then go back to this side.
So what are some of the ways in which NREL does collaborate with the private sector?
Well, so our charter has always been, my job mission is the technology gets developed, but otherwise has to get developed, integrated, and adopted. So we're not done until the energy mix changes. Okay, so that's kind of the issue. So we've recognized way from the beginning that it's about partnership. Unless we do this in partnership, you know, doing the great science in the lab and going over the wall, hope some good things happen, that doesn't work. It just never has worked, never will work. Certainly not in this sector won't work. So we do a lot of things. We do collaborations with industry. You know, our charter, the reason we're given money is to do R&D typically. All right. Now we've broadened that a little bit because we see the problems with trying to get to the endpoint, needing all these other component things. So we do analysis, analytics, as you've seen, and a variety of other things that relate to the integration, because that's the next big thing in my mind. And so it's all about partnerships. We do everything we do in partnership, both with the university, the academic community, as well as with the private sector. And so we have a lot of work that we do kind of, you know, essentially where we seed things and start them internally, but ultimately almost everything we do, almost across the entire $300 million of R&D that we do is in partnership with somebody or with some institution or entity. So it's hard to answer the question other than we create research and development agreements and a variety of other things.
Do you sell patents that you develop to the private sector? How does R&D get from you to end use?
Good question. All right, so the technology typically flows. So we'll patent something and do something. Let's say we do it by ourselves or in collaboration. I'm responsible as the laboratory manager to see that technology gets licensed in the marketplace. And so we'll do an agreement with somebody and either license it exclusively or not exclusively, and then try to make sure that that's the best way that technology gets deployed. And so we're managing the government assets. Government pays for our work. Those become government-owned intellectual property. We manage it on behalf of the government. I take ownership of it, you know, by contract. I take ownership of it, and then I manage it as if I were a portfolio manager. I'm not trying to maximize revenue back to the lab because, you know, again, my job is to make sure the technology gets used. So we'll tax success, but I don't want to make it so burdensome on the entrepreneur who's out trying to do stuff by you know, saying, all right, you got to put a lot of money down to begin with. We'll tax success. If they're successful, we'll hope some comes back to the government and we'll manage that accordingly. But typically we do an intellectual property management, like Stanford does in their business schools. All right, let me get back over here. Yes?
So I have a question about decentralized energy distribution systems. One of the biggest issues in the United States is the NIMBY problem, not in my backyard. that happens a lot, reminded me, because of wind generation. How do we address that? Because that seems to be a public education issue of sorts.
Yeah, and that's a tough one. It's a social issue, and it's a values issue, and some people, in Texas they like oil rigs, and in Massachusetts they don't. So, same with wind turbines, except it's the other way around. I think there's lots of things that one can do. If you talk about offshore wind, we can put the turbines farther offshore, so then you don't see them and everybody's happy. There really isn't an issue when it comes to things like migratory bird patterns and radars of airplanes. I mean, those are all hype. In my opinion, again, they're all hype kind of things. Problems that can be solved, right? We kill more birds in stationary buildings than we kill, with some of these projections about how wind turbines would operate. But that's really not so much the issue. The issue is it's a value judgment. And the question that, again, back to the public and the public's perception is, what do you want to get your energy from? And if you think, several years ago, I was in a university class, and some little gal said, well, I don't want to burn coal, I just want electricity, And I said, well, they kind of go together. And in this case, once you know that you burn coal, then you ask the question, would I rather burn coal or would I rather use the wind? And maybe it isn't an either or sort of answer, but at the same time, there's a lot more that we can do in public perception. If you go to Europe, you don't have some of these kinds of discussions. I mean, you do it, but to a larger, much smaller degree. And that has more to do with the fact that they've embraced the idea that we have a renewable energy future, and it's really important, we're going to get to 100%, and by the way, we're not going to use nuclear. That's what they say in Germany. I'm thinking, really? Wow, okay. And they think they can do it. And they have an infrastructure, and they have a cost system, and a set of business values that are encouraging that outcome. And as a consequence, they have 18 megawatts of PV, or 18 gigawatts of PV. I think all of those things really relate to what is that national energy strategy? What do I want? What do I want to achieve? And how am I going to get there? And until we're on the same page on that, not much is going to happen. And a lot of that, in my opinion, is public awareness. One more question. Yes, right here.
So you've spoken a lot about sort of distributed generation, and you had the map up there that we have to have different kinds of generation from different areas. But you were talking about local policy a few minutes ago, and it seems that if Southern California decides that they want to use solar, but the rest of the country doesn't, sort of sticks with fossil fuels, that vision might not be realized in such a strong way. So how do you influence local policy at a national level that everyone's supporting one another?
Yeah, it's a little bit of a iterative process. I think what my experience has been is that local grassroots efforts, when they aggregate together in broad ways, they force the more central policy to actually conform. And so you don't get Washington leading so much as you get the heartland leading, and it kind of pulls it together, and then Washington runs to get in front of the parade. So it gets they'll take credit, but the fact is that it happened because it made it politically less of a challenge for them to get on board. And I think that's probably what will happen here. Part of what we've done over the course of the 100 years of previous government intervention in our energy system is we put a patchwork of regulations and jurisdictions together. You got all these overlapping things. You got 20 people that have to get together and say yes. And until everybody kind of wants to do it, it's not going to happen. So you have to kind of solve those problems locally. And if you get the central government coming in and telling all those 20 groups, okay, by the way, we're going to do it like this, that causes chaos. And I think short of some sort of a government intervention like we had with the highway system, where they said, really what we want to do is we need a highway system that allows us to move troops from the East Coast to the West Coast, and it's a national imperative, and we're all going to get on board, and everybody's going to do that, and we built a highway system on the basis of national security. Well, if we had something similar to drive that centralized big government approach, that would work. In this area, it's uniquely a market-driven sort of thing. It's not a until it becomes a national security problem or something like that. I don't think you'll get the big government intervention. And so it's going to have to be done in pieces, I think, again, in aggregate, and then ultimately it'll flow up and we'll get government policy. And the opposite of that, of course, is what happens in China. They have more, essentially centralized government. Everybody says march, they all march. Sometimes they march in the wrong direction, and that's always not a good thing either. So, the two systems are different, and you'll get different outcomes and maybe at different rates. But I think it's going to be more grassroots up and down. Thank you.